One element from section 9.2 I didn't discuss, and I think this is kind of a nice example of working with permutations. So I should have. So the setup in this example they give is this. You've got a table, a round table, with 6 positions at it, 6 chairs. And there's a group of 6 diplomats who are going to come and sit at this table and talk about, their mutual needs. The design is so that nobody, there's no head of the table. It's sort of a circular table, so nobody gets, feeling a loss of status because they're not at the head or close to the head or anything. It's making everybody be sort of treated equally. So how many ways are there to seat these people? And the point is, it kind of doesn't matter if I seated them as A, B, C, D, E, F. That would be fine, but if I started here and did A, B, C, D, E, F, honestly, that wouldn't be different. That's the same relative positions, just physically they've been moved over. It's like they played the game musical chairs, right? Where everybody stood up and shifted around and sat back down. That's not truly a different seating. So here's the argument. You might as well pick somebody and say, wherever they are, we'll consider that the head of the table. Right? And if I'm going to call them A through F, then I'll say A is the head of the table. So A is going to go in this position. We'll make that a caveat. Right? We'll just say that's the case. We'll put A at the top. If A is not at the top, we'll shift the thing around until A is at the top. And then the question remains, how many ways relative to A can we seat the rest of the diplomats? Well, once you've selected that guy and made it fixed, it's just how many choices for here. We had 6 people, one of them's been seated at the head, so there's 5 possibilities for there. Then 4, 3, 2, 1. So the number of cyclic permutations, that's what these are called, of 6 things is 5 factorial. And if you feel like generalizing this, it's really easy to do. If there were n things, turn that 6 into an n, then instead of 5 factorial, we would have n minus 1 factorial. Okay, so that's the tail of 9.2 that I forgot about. In section 9.3, we start off with something called the addition principle. I love the way they name these things, by the way. It's going to look at the multiplication principle for the scenarios in which you multiply. And then we've got the addition principle for the scenarios in which you add. I feel like they could have come up with more imaginative names, but they didn't. So, what is the addition principle about? It basically says that if you have a set that can be partitioned, I'm going to say this in a slightly different terminology than they do in the book, by the way. In the book, they just say, look, you've got a set that's a union of things, and the things have, but there's actually a name for that phenomenon. So why don't we just use it? A partition of a set a partition of a set is a collection of subsets. I'm only using the word collection here because I feel like it sounds weird to say a set of subsets, but it is indeed a set. A collection of subsets. I guess they're subsets, so let's call them S1, S2, up to SK, say there's K of them, right? Such that what you want out of these subsets is that if you take the union of all of them, you'll get the full set. Oh, I didn't put a name on the set. I'm sorry. Let's come back and fix that. A partition of a set, comma S, comma, is a collection of subsets S1 through Sk such that S is equal to S1 union S2 union S. Well, let's just throw some dots at this. You get the pattern, right? You're going to union up all those things, and the last one being Sk. But there's one more proviso, and I'm not sure if I get, well, maybe I can fit it on here. If you look at any pair of these sets, Si and Sj, say, their intersection is empty. So for all ij, how do we say that? For all 1 less than or equal to I less than j less than or equal to k, so pairs of numbers that are different in there, in the range between 1 and k, S sub I intersect S sub j is the empty set. So it says these k subsets here are disjoint from one another. They have nothing in common, and their union is the entirety of the set. That's what a partition is. And what the addition principle finally says about partitions is that you can figure out the size of the set S by just figuring out the sizes of all the sets S1 through Sk and adding. That's addition. Right, so I'm just rewriting addition principle smaller so I got the room to say what it says. And it says it in terms of the language you're using right here about partitions. The cardinality of the set S is equal to a sum, where I goes from 1 to k, of the cardinality of set Si. So add up all these guys' sizes, add up all of their sizes, you'll get the size of the set S. Let's put that in practice for a couple of, well, at least one small example. I think most people have pins for like a credit card or a bank card, or sometimes you have pins for other things, log into an online account. I was finding it amusing that so many people say pin numbers, because the N stands for number. So anyway, pins for a bank consist of 4 to 6 digits. And the digits are the ordinary digits, 0 through 9. So you can put them in on almost like a telephone style keypad. So how many pins are there? Well, we're going to use two things actually. We'll use the multiplication principle to figure out how many there are of size 4, how many there are of size 5, and then how many there are of size 6. And then we'll use the addition principle. We'll add those things together. Would you say this is a partition? We're talking about, the full collection of the pins, wow, that would be ridiculously large, but it would look something like this. You have 0, 0, 0, 0. That's a terrible pin to choose. 0, 0, 0, 1. That might be a good one to choose because it would, somebody wouldn't notice that the final digit was different than what they thought, and maybe not guess it. Well, 0, 0, 0, 2, blah, blah, blah. There's a lot of ones in this line, and then there'd be another row that starts with 0, 0, 0, 0, 5 of them, right? And then 0, 0, 0, 0, 1, and both of these things go quite a long distance. And finally, we'd have the next line of things would be the 6-digit pins that would begin with 6 zeros. I actually knew somebody who did this. That's why I'm sort of making a joke to myself. But having an actual identification number, a password essentially, that's all the same digit is, particularly stupid. Especially for this kind of thing where you might be entering it into a bank machine in public. So if somebody sees you putting in something that they can tell is a really obvious thing, they're gonna hit you over the head and take your card and your money. Yeah, so anyway, but the point is that we can count these 3 rows and then we can get the total by adding up how many are in each row. All right, so let's do it. How many pins are there that have 4 digits? Well, that's a case for the multiplication rule, right? The number of ways we have of choosing the first digit is 0 through 9. That's 10 of them. And the number of ways we have of getting the second digit, I mean, yeah, I'm already showing that it's possible to have repeats, so I guess I have 10 possibilities for the second digit too. In fact, it's 10 times 10 times 10 times 10. 4 tens. This is 10 to the 4th. That's our 4-digit pins. 5 digits, maybe I can just cut to the chase here. 5-digit pins would have 10 to the 5th. And 6-digit pins would be 10 to the 6th of them. So what's the total? Total is 10 to the 6 plus 10 to the 5 plus 10 to the 4, which is 10 to the 4 is 10,000. So it has 4 zeros after it, and then there's the 10 to the 5th, and there's the 10 to the 6th. So it's right like that. 1.11 million possible pins. Nice. Now, this business with pins actually shows another way in which you can use the multiplication, the addition principle, but you're effectively using it in reverse. So I would say this isn't really a new idea, it's just using the addition rule backwards, but in the book they talk about the subtraction principle. So this is most often used in a scenario where you have the set S is equal to the union of just 2 things. And the 2 things are disjoint. Okay, so that's a special case of a partition, just two subsets whose union makes the entire set and that are disjoint from one another. They have no intersection. And what the subtraction principle says is you can figure out what the size of either of these is if you know the other one. Right? So that is the size of, let's say, A is equal to the size of S minus the size of the other set, which is B. So when you have this sort of scenario where a set can be divided up into 2 subsets, if one of them is easy to count, then you get the other one for free. You can figure out the other one. So an example of this would be in order. And let's go with pins again, but just 4-digit pins. Because we know how many of them there are. We already did that. There's 10,000 total. You can divide these 10,000 things up into 2 groups, one of which is the ones that have some digits repeated, like the 4 zeros thing, but not necessarily that. I mean, it doesn't mean that they have to all be the same, but rather, it might be 9, 8, 8, 4. It's got 2 8s in it, so that's a repeated digit. So we'll let A equal the pins that have repeated digits. Can I just say repeats? You'll understand what I mean. And B is the pins with no repeats. Now, one of these 2 is easy to count, and the other, well, like I said before, you get it for free because you can count the first one. We know we've got 10,000 total. Which one is the one that's easy to count? Turns out B is. It's not hard to count the number of choices from 10 things where you're not allowed to have repetition. It's just that's really a permutation number. It's 10, pick 4. The number we would call P of 10 and 4 gives the, what am I saying, the class that are, I'm sorry, B, gives the size of B. Right? It's the ones that have no repetition, because P of 10, 4, just remember what that means. It's 10 times 9 times 8 times 7, a descending product starting at 10 with 4 terms in it. Why do I know that? Well, think about, you've got 10 choices for what digit goes first, but because there's no repeats, you only have 9 choices for what goes second, and 8 choices for the third, and finally 7 for the last. Cool. So this number is, I guess I should have calculated that in advance. Let's see, 10 times 9 times 8 times 7. 5040. So there's 10,000 in total, and there's 5,040 in B. We do this subtraction. I'm not sure why I need a calculator to subtract this. I probably should have just done it in my head. Is it 40, 60? Whoops. Oh, yeah, I would have got it wrong. It's 4960. So the conclusion you get is the size of set A, that is the ones that do have repeated digits in them, is 10,000 minus 5040. Which is equal to 4960. The restriction that you put on a partition is pretty severe. That is, you try to find a collection of sets that whose union is the entirety of the set you're in, and that have nothing in common amongst one another. They're disjoint. Partitions are hard to come up with, and you don't necessarily need to have a partition to be able to count stuff. So the result that lets us count things in more general situations, that's called the inclusion-exclusion principle. And it's really nice. You don't need to have this, like I said, difficult thing maybe to come by, the partition of the set. So suppose you have S is equal to the union of two things, A union B. Then what a lot of people think is true is this, that you would just take the number, to find the number of things in S, you would take the number of things in A and add it to the number of things in B. But that's wrong, right? That's what we just saw. That would be the addition rule, and that requires A and B to be disjoint. But they need not be, right? They might have something in common. So what we're doing is including things in A and including things in B, and then we will exclude things that are in both. So we'll take away the things that are in A intersect B. And that'll be a correct count. So think about how many times an element gets counted. I think it might help us to think about a Venn diagram here. Here's set A. Here's set B. The union is everything that's in either of these circles. If I'm in this region, then I get counted by that once, right? I'm not going to get counted by the B, am I? Well, if I'm in this region, I'm not in B. B is everything inside that circle, so no. And I'm not going to be in the intersection. The intersection is this football-shaped thing in between them. So if I'm in here, I get counted by that term and I get counted once. Similarly, if I'm on the outside here, I get counted once. The only thing that's tough to figure out is how many times does somebody who is in there in the middle get counted? They get counted once amongst these things, because they're in A. They get counted again in B, and then we take away one. So it was 1 plus 1 minus 1. Which is 1. Right? So the point is that everything in this sort of shaped, hourglass shape, I don't know, like the viewed through binoculars shaped region gets counted once. So that is indeed the count of the size of the union. Awesome. Let's try to put that to use. Do a quick example of using inclusion, exclusion, just with two things like that. Let's think about the dog shelter. There are, say, 40 dogs that have fleas. And there are 30 dogs that, what else can be wrong with the dog so that we wouldn't want to send him out to be adopted? Behavior problems, I guess. No, I don't want to talk about dogs with bad behavior. How about they have mange? That's a terrible skin disease that some dogs get. We would never have 30 of them with it, but whatever. And suppose there are 50 dogs. So wait a minute. I don't want to. There could well be dogs that don't have anything wrong with them. So I don't really want to say that there are 50 dogs total. Excuse me. That's not quite right. There are 50 dogs that have one of these problems. There probably indeed are dogs that have neither fleas nor mange, and you can put them up for adoption. Right? So this is the question I wanted to get at. We've got 50 dogs with problems. 40 of them have fleas, 30 of them have mange. What can I figure out from this? Well, if you think about this is the set A, or really that's the number of the set A, and the next one is the set B. Then that 50 there must be equal to the size of that one plus the size of that one, minus the size of the intersection. So what I'm getting at here is that you can figure out how many animals have both problems from the fact that there are a total number of 50 of them, and we know how many have each of the individual problems. You can have the unknown quantity be in any one of these spots, right? We could have, I don't know what the total is, but I do know all three of these numbers, or I could have, one of those is missing. But I picked on the one where we didn't know in advance what the number in the intersection was, and now we can figure it out. Because that adds up to 70. What we're subtracting here must be 20. Let me do, let me show you the next phase up in in the inclusion exclusion principle. This was where we were just dealing with pairs of sets. The next stage up is if there are 3 sets. And then there are sort of more ways that they can be overlapped. So actually, I think probably most of you have seen these sets diagrams before, these Venn diagrams for 3 sets. Here I might have A, B, and C. And what the inclusion-exclusion principle says for 3 sets is this. You're trying to figure out the size of A union B union C. And a kind of a first stab at it is to add up the sizes of the sets. So add up n of A, n of B, and n of C. But that way overcounts things, right? The things that are in the intersections. So for instance, if I'm in this region right here, which is the overlap between A and B, I've just been double counted. So I've got to take those away. In fact, what I want to take away is all of those intersections. That's A intersect B, but we'll also want to remove, I'm going to group these so that we'll subtract them all at once. N of A intersect C, and finally N of B intersect C. Sorry, I'm at the edge of the board. And then there's one more parenthesis that there's really no room for. Okay. So I start with all the sets, their sizes, then I subtract out all their intersections. What's wrong with this? It comes down to these things have been counted properly. Sorry. If I just think of what's not in set C, the A and the B and their intersection that are not part of set C, I've got those things counted correctly because I've added them and then I've subtracted them. And similarly for that region and that region and that region. But this little Wankel rotary engine looking thing that I've got in the middle there, this sort of a rounded triangle, it's actually got a name, by the way. It's called a Rouleau triangle. Rouleau is a French engineer. That has been counted, well, the wrong number of times. So think about how many times you've counted something that's in this intersection of all 3 sets. You counted it once here, and here, and here. You've counted it 3 times there. Oh, great. Then you've taken it away once, twice, and 3 times. These things in the middle haven't been counted at all yet. So we're going to need to throw them in. All right, let me take away those little stray marks. We need to add back in the size of the intersection of all 3 sets. So that's the inclusion-exclusion principle for 3 sets. We include things in the individual sets, then we exclude things in the intersection, then we have to re-include things in the intersection of the intersection, the 3-way intersection. I'm going to return to the dog pound here, and we're going to work out the total number of dogs this time, the total number of dogs with some issue involved. So A is going to be, they have fleas again. B is going to be, they have the mange again. And C is going to be the bite. They snap at people. Can't put up dogs for adoption if they are going to bite people's little kids. So you have to, they can be trained to stop. Anyway, now I'd also like to think about what the intersections are. So what does A intersect B? Well, those are very unfortunate dogs. They have fleas and they have mange. And what are the other intersections? How A intersects C? These have fleas and bite. And finally, B intersects C. These are animals that have mange and also bite. And finally, we could have really bad dogs, not bad dogs, they're all dogs are good, but dogs in bad condition that have all three issues, right? Mange, bite, and fleas. Fleas, bite, and mange. Can I just say all three? Poor dogs. All right, so I'm going to give you some numbers for these things. Suppose there's just one like that has all three issues. There are two that have mange and bite, and there's one that has fleas. Well, let's make it two again. Two that have fleas and bite. And finally, there's three that have fleas and mange. Yeah? And then there's a total of 8 that have issues with biting, 11, that's a lot of dogs with mange. It's actually kind of a rare condition. And how about 19 that have fleas? Can we work out how many dogs there are total? How many dogs have that need to be dealt with before they can be adopted? Well, the inclusion-exclusion rule says that the number of things in this set is, you add these guys, so it's 9 plus 11 plus 8, and then you subtract out the ones, the pairwise intersections, so that'd be 3 plus 2 plus 2. And then you add back in the single one, the three-way intersection. So that would be 28 minus 7, 21, plus 1, 22, according to my calculation. I'm going to illustrate this on a Venn diagram. So I'm just going to need to save the sets and the numbers. I think we all can deal with the descriptions being erased. Okay. So, 3-set Venn diagram with A at the top, B over here, and C on this side. And you can basically number all these regions based on how many things are in them. If you sort of start at the inside and work your way out, you'll be able to do it nicely. So there was one thing that was in the intersection of all 3 sets. There were 2 that were in B intersect C. Well, B intersect C is this region, this football here between B and C. And there's already one thing in it. So if there's 2 total, there must be 1 more in that part. Similarly, this was AC, I believe. So this football region between A and C has to have 2 things in it. It's got 1 already because of the 3-way intersection, so 1 more in there. And for A intersect B to come up to 3, we've got 2 that are in there. So just check me on this. The intersection of A and B has 3 things. The intersections of A and C have 2, and B and C have 2. And 1 thing in the full-on intersection. Now, how many things are supposed to be in A? 19 all told. And we've got some of them. We've got 4 things already in A. So what's out here that these would be the animals that just have fleas and none of the other issues. To make this all tally up to 19, there have to be 15 in there. Okay. B was 11 things, and we've already got 4 of them, so that means 7 more that are outside of the other 2 sets. And finally, C, these were the bitey dogs. There's 3 of them that also have fleas or mange or both. And then that means we have 5 more that's their only issue. So, if I've done this right, we should be able to add this stuff together and get 22. 8, 9, 10, and what's 15 and 7? I just got 32. Not 22. Did I go wrong somewhere along the line? 28 minus 7, that's 21. Oh, I did. I found I found where went wrong. I guess it's instructive. I was off by 10, and I was like, wow, that's a lot. And I see now where I went wrong. It was in this part right here. I just copied the number wrong. That first digit, that first number should have been a 19. And when I was working out this, I was using 19, but when I was working out this, I was using 9. So this was incorrect. Should have been a 32, and that's what we got when we tallied this stuff up. Woo. All right. I hate it when I make mistakes, but I'm pleased when I'm able to find what went wrong and fix it. So, you know, I guess that's a life lesson of some sort. The next thing we're going to talk about, I think this is 9.4, maybe it's 5. 4, I was right in the first place. It goes by the name of the Dirichlet-Box principle. That's spelled D-I-R, well, I have it written on the board, you'll see it in a second. But Dirichlet was a French mathematician, more commonly called the pigeonhole principle. I'm going to illustrate it with these 3 bowls. And what I've got here are the 4 markers that I've been using. Here's the idea. If I've got 3 containers, but 4 things, and I'm going to put the things somehow into containers, one of these containers has more than one thing in it. That's the whole point. It's not a piece of genius. It's an actual real common sense idea. It doesn't matter how I stick these things into containers. I could put 3 of them in there, 1 of them in there. Well, that one's got more than 1. That's got 2. The best I can do is sort of put 3 of them individually into single bowls, but then I've got this one to do something with, and so no matter what bowl I put it in, I create a full thing. When they talk about the pigeonhole principle, they say if n plus 1 pigeons fly into n plus 1 pigeon. Wait, just said that wrong. Back up. N plus 1 would be the pigeons. These things are like the pigeons. Fly into n holes, then some pigeon hole must have 2 birds in it. I don't know. I'm not sure I've ever seen pigeons going into holes, but boxes I understand. So I prefer the Dirichlet-Box principle versions of things. So for the not centered, there's the spelling of Dirichlet. Oh, I'm having trouble centering this. Okay. Dirichlet-Box principle, also known as pigeonhole principle. I'll write it out since if n plus 1 objects are placed, put into n containers, then some container must hold 2 objects. Now the containers can be sort of metaphorical, if you will. For instance, a nice example of this is if you have 13 people in a room, there are 2 of them that were born in the same month, for sure, right? That's because the 13 people would be the objects. And I'm not talking literally about putting them into containers, but I might think about categorizing them based on what month were they born in. There's 12 months, so 13 things into 12 containers means 2 of them are born in the same month. You do that same thing with astrological signs. If you have 366 people, okay, maybe sometimes it's leap years too, so definitely if you have 367 people, you're guaranteed that there's going to be 2 people that have the exact same birthday. Not necessarily the same year, but the same month and day. And that's the same thing, the Dirichlet box idea. The people are the objects, the containers are the day of the year that they're born in. So the book has an example of this. They say there's 2 people in New York City that have the same number of hairs on their head, which I think is cute. But you can extend that. Well, let's deal with that issue. How could we possibly know that there are 2 New Yorkers with the same number of hairs on their head? It's nuts. We would put the people would be the pigeons again, and the boxes would be the number of hairs on their head. Now, I don't know how you could ever discern how many hairs are on somebody's head, unless they are like me, where they're bald. You can say, okay, 0, but most people you'd have to shave all their hair off and then count all those things. Maybe some good AI photo recognition program could do the counting. It seems impractical, right? But here's what we can do. We can estimate how many hairs there are on a human head. And the estimation is not bad. You have to just think about how much square area there is and count up how many hairs you find in a typical square inch and then multiply. And it's about 1 million. There's approximately 1 million hairs on a head. Well, how many people live in New York City? It's like 8 million, I think. So way more, right? So there's way more people than there are maximum possible hairs. Maybe there's some people with really thick hair, and a couple of them have 2 million hairs on their head. If everybody had somewhere in the vicinity of 2 million hairs on their head, that wouldn't be enough, because the number of people in New York is so much larger. So the oddity of the Dirichlet box principle, or the pigeonhole principle, is that there is no way for us to figure out who these 2 people are that have the same number of heads. In fact, there's probably lots of people that have the same numbers. We'll never know who they are, but the principle isn't about that. The principle is about guaranteeing that such a pair of things exist without being able to figure out who they are. It's what's known as non-constructive. We don't know who the individuals are, but we do know that there are a pair of them. So that's a fun example. One that I have taken to heart myself comes from, well, it's a silly question, really. So it was posed to me by my thesis advisor back when I was in grad school, and I probably should have known the pigeonhole principle when I was already in grad school, but I really didn't know it that well. So she says that she has 20 purple socks and 20 black socks. I forgot the word. Maybe I ought to say pairs of. And 20 pairs of black socks. That's the strangest way to spell black I've ever done. Okay. Black socks. Okay. So there's a total of 40 purple socks and 40 black socks. And she had this story, which I actually don't quite believe. She gets up pre-dawn, right? It's dark. She doesn't want to turn on the light in the bedroom because her husband's sleeping. So she has to grab some socks and take them into the bathroom to change, to get dressed. And so the question is, how many socks should she take? we don't want to have a mismatch, right? So we want to make sure that you can either wear a pair of black socks or a pair of purple socks. And the answer I guessed originally was 41. Because if by terrible bad luck you got all black socks and then you didn't have any purple socks, oh, maybe sorry, I was smarter than that, I guess 42. Maybe you picked up all the black socks, and so there's 40 of them, and then 2 more socks, that guarantees you got a couple of purple socks. I think she was literally wearing purple socks that day. But that was dumb. It was dumb, wasn't it? Because my assumption was that she wanted to get purple socks. She didn't care about that. She just wanted a matching pair. So this is not correct. Who knows what is correct? Are you guys guessing this right now? The answer is 3. That's all you have to do. Grab 3 of them. If 2 of them are black, you're done. If 2 of them aren't black, then the other 2 of them are purple. You could have 3 black. That's perfect. You got 2 black, 1 purple. Still good. You can got a black pair. You have 1 black and 2 purple. Now you've got a pair that are purple. You can have 3 purples. Awesome. Right? No matter how you think of 3 socks being distributed amongst these 2 colors, you only get you get a pair so long as you've got 3 of them. How can we say that in terms of the pigeonhole principle? Well, the pigeonholes, the boxes, would be the colors. So we've got a purple box, and then we've got a black box. And when she gets into the bathroom and can see what color they are, she throws the purple socks in that box and the black socks in that box. So how many things do we have to have in order to get, one of these boxes full? 3. There's 2 boxes. N plus 1 is 3 in that case. There's some extensions to the pigeonhole principle that we should look at. Oh, wait, before we leave the basic pigeonhole principle, I wanted to mention one example that's not just playful like these have been, not just sort of recreational math. A real example. You want to select 6 numbers from the collection of things that goes from 3 to 12. All right, so select 6 numbers out of 3 through 12 in any way you like. Must there be 2 that add up to 15? Well, that's a strange question, but it turns out the answer is yes, and we can use the Dirichlet box principle to see this. So what will the boxes be? We get to make up we get to choose what the boxes are going to be. Because we're selecting 6 numbers, I think that gives you a clue of how many boxes there would be, right? I want to make 5 boxes, and these 6 numbers are going to go into them, and having a pair that are in the same box is somehow going to tell us that those guys add up to 15. So maybe I don't need to sketch all these boxes so accurately. 1, 2, 3, 4, 5 boxes. I'm just showing you the front faces of all of this. 3 is going to go in some one of these boxes. So if we get a 3, we'll put it in this box. And if I want the 2 things that happen to be in this box to add up to 15, then the other thing I would put in this container would be 12. So if I get a 3 or a 12, I'm going to put it in the first box. 4 and some other number will go into the second box. Now I'm feeling like I want to sketch the box anyway. What's the second number? I want there to be 4 and something that'll add up to 15. Oh yeah, 4 and 11. And then 5 and 10. And then 6 and 9. And finally 7 and 8. So all the numbers are taken care of, right? 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 3 through 12. So every number is going to go into one of these. If one of these containers has got 2 things in it, though, we've found 2 things that add up to 15. So this idea of sort of engineering the boxes so that it does the thing you want is kind of clever, and makes nice use of the pigeonhole principle. There's a nice generalization of the pigeonhole principle that comes about by thinking about this issue. What if the boxes you're looking at could hold more than just 2, right? The pigeonholes are big enough that might have 5 pigeons in one hole. In fact, that's the scenario I've drawn. Each of these containers is capable of holding 5 objects. In fact, the first one has actually got 5 in it, so maybe we'll take one out of there. I want them to not be all the way full. How many objects would we need to spread out amongst these containers in order to be sure, though, that one of the containers was full? This is thinking of the original pigeonhole principle as being containers of size 2. So getting 2 birds in the same pigeonhole meant that container was full. These guys are containers of size 5, and full would mean having 5 things in one of them. So the answer is pretty easy. Think about what's the most number of objects you could have, and yet nobody's full. The most you could have is everybody has 4 in it, right? So if I have one more than this, you got this one more guy, where are you going to put it? No matter where you put it, you're going to create a full container. So let's speak in generality about that. Suppose there are k containers, or k boxes, each having capacity m. Then what did I figure out? Take 1 less than the capacity and multiply by how many boxes there are. K times m minus 1. That was supposed to be an m. M minus 1 plus 1. If k times m minus 1 plus 1 objects are put into these boxes, some container will be at its capacity. I'm going to try to turn this into a better sentence. Then, if that number of objects are distributed amongst the boxes, and really, I should emphasize, this distribution is arbitrary. You can do it any way you want. Well, the conclusion is some box must hold m objects. I think I just want to read through that whole thing one last time. Suppose there are k boxes, each with capacity m. Then if this special number, k times m minus 1 plus 1 objects, got an extra of in there, k times m minus 1 plus 1 objects are distributed among the boxes some box must get M objects. In other words, it's at its capacity. So that's it for today.